In this video, I'm going to mention matrix representation of a graph. We know how to represent graph geometrically. Now, for that geometric representation, we write the matrix for the particular graph. So, we can represent a graph by using a matrix, and we can write different matrices for the particular graph. So first matrix is incidence matrix. If I have a graph G with n vertices and E edges, and there is no self loop, then I can define a matrix of order, say, n cross E, where n is number of vertices and E is number of edges. A graph with the order n cross E in such a way that, say, matrix is represented as A of G, which is the incidence matrix of a graph G. Then the entry, say I'll mention entry as, say, some Aij. Matrix is of order n cross E. Then each entry Aij is 1 if jth edge, because n represents number of vertices, E represents edges. So first entry means it gives you the number of vertices. Second entry gives you edges. So if jth edge is incident on ith vertex. If jth edge is incident on ith vertex, then the entry in incidence matrix is 1 and 0 otherwise. So such matrix is called incidence matrix or edge incidence matrix, and is denoted by A of G. So we'll give you one example. Suppose I have a graph . A, B, C, D, E and F. Okay. These are the vertices, and I'll name the edges, say E1, E2, E3, E4, E5, E6. Now we'll write incidence matrix for this graph G. Okay. A of G is equal to, first I'll mention all the vertices. Vertices are A, B, C, D, E, F. And edges E1, E2, E3, E4, E5 and E6. So let us write the matrix. If ith edge is incident on jth edge is incident on ith vertex, then the entry is 1. Let me take first edge, that is E1. It is incident on the vertex A and vertex B. Okay, so rest all the entries are equal to 0 because it is not incident on any other vertices. and when I take edge E2, it is incident on B and C. B and C. So rest equal to 0. E3, C and D. C and D. So rest 0. Then E4 is again on C and D. E5, E and D. E and D. E6 is on B and E. Rest entries are equal to 0. So this is the incidence matrix for this graph. So then it contains only two elements, that is 0 and 1. Why? Because we are taking these elements from the Galois field modulo 2, and why I am getting only entry 0 and 1 is because each edge is incident, it can be incident only on two vertices. So the maximum entry will be 1 and the minimum entry will be 0. So in fact these two elements are from Galois field modulo 2. Now from this incidence matrix, we can observe few things. Okay, so first observation is it has got every edge in incidence matrix is incident on exactly two vertices. Okay, so such column of incidence matrix has exactly two ones. Okay, every edge is incident on two vertices, therefore every column in the incidence matrix has got only two ones. You can observe this 2, 2, 2, 2, 2, 2. I'm sorry. E6 is incident on B and E, right? Okay, I'm so sorry. So first observation is every edge is incident on exactly two vertices, therefore each column of A of G has exactly two ones, and the number of ones in each row represents the degree of that corresponding vertex. See here, vertex A is of degree 1 and number of ones in that row is also 1. And if I take C, here number of ones are 1, 2, 3. You can observe here degree of C is 1, 2, 3. Okay. A row with all zeros corresponds to isolated vertex. Here this F, vertex F is of degree 0, therefore every entry in the A of G is 0. Parallel edges in a graph produces identical columns. See, parallel edges, that is parallel edges represent identical columns. When I take E3 and E4, they are parallel, you can observe. So from this matrix also you can say these two are parallel, therefore they are identical. If I have a graph, if it is having two components, say G1 and G2, graph has got two components, say G1 and G2, then the incidence matrix of this graph A of G can be written in the block diagonal form, that is A of G1. This full block represents component G1 and this is A of G2. So this full entries represent a component G2, this full represent component G1. We mention this as block diagonal and this representation is called block diagonal form. This is for the component G1 and this is the incidence matrix for component G2. And if I take a permutation of any two rows or any two columns in an incidence matrix, that simply corresponds to relabeling of vertices and edges in that graph. And if two graphs, if I say G1, mu1, mu2 or G1, G2, if they are isomorphic, then their incidence matrix differ only by the permutation of rows and columns. Next is theorem. In fact, we are going to find the rank of incidence matrix. A of G is the incidence matrix of a connected graph G with n vertices. Then rank of this incidence matrix is equal to n minus 1. So let us see how it is. Each row in an incidence matrix can be regarded as a row vector over the Galois field because the entries are only 0 and 1. So each vector here, each row I can represent as, I can take it as a vector over the Galois field 2. That means I'm representing graph, I'm taking a vector space of a graph, and there I'm taking each row as a vector, row vector. Okay, so I can represent that incidence matrix like this. A of G, each row I'm taking it as a row vector, say A1, A2, like that. There are n vertices, so n row vectors I'm considering. Okay, first row be A1, second row it's A2, like that. Since I know that there are exactly 2 ones in each column, okay, when I take an incidence matrix, in each column exactly 2 ones. Therefore, when I take sum of all these vectors and I take modulo 2 because I am defining this vector space over Galois field 2, right? So, sum of all the column vectors by taking mod 2 gives me the value 0. Okay, so I can say that these A1, A2, AN are linearly independent. Say for example, if I take 1, 0, 1, 0, 0, 1, 0, 1, 1, say suppose they are parallel. This represents edges and this represents vertices. Now when I take sum of these column entries, say 1 plus 1, that is 2, 1 plus 1, 2, 1 plus 1, 2. But when I'm defining over modulo 2, therefore the sum of the entries will become 0. Therefore I can say that this is this particular, I can say these vectors are linearly independent. Sorry. So, right, since there are exactly 2 ones in every column of A of G, the sum of all these vectors is 0 when you take, then modulo 2 is applied. So I can say the row vectors A1, A2 dash dash, AN are linearly independent. We know that rank of a matrix means it's a number of linearly independent rows. Therefore, I can say that rank of A of G, which is equal to number of linearly independent row, which must be less than n in this case. I can even write it as less than or equal to n minus 1. What does it imply? Rank of A of G can be at most n minus 1, is at most n minus 1. So let me call this as statement 1. Now, if I consider sum of any m of these row vectors, okay, where m is less than or equal to n minus 1, any m of these row vectors, if I take their sum, then I can represent, I'll write now, say sum of any m of these vectors, these n vectors, where m less than or equal to n minus 1. Since the graph has exactly one component, we can't find any m cross m submatrix such that modulo 2 sum of these m rows is equal to 0. See, it's mentioned that graph is connected. If it is disconnected, then can be partitioned into it can be partitioned, and I can write it in a block diagonal form, right? But this here has got only one component, so we cannot find any such m cross m submatrix such that modulo sum of these m rows gives me 0, right? This here in this, if I take any m cross m, if I take, then modulo sum won't be equal to 0. Because of connectedness of a graph G, I cannot find any such m cross m submatrix, so whose modulo sum gives me 0. So that is same as saying, since there are only two entries, zeros and ones in any row, no linear combination of m row vectors can't be equal to 0. Okay, so I cannot take any m such rows who their linear combination gives me 0. Hence I can say that these n minus 1 rows are linearly independent. Therefore, consequently, I can even say rank of A of G must be at least n minus 1, must be at least n minus 1, because if I take less than n, then that gives me the submatrix. In fact, they are linearly independent, so rank must be at least n minus 1. So we have already taken the first statement that rank is at most n minus 1, equation number 1, and here rank must be at least n minus 1. Therefore, from 1 and 2, rank of A of G is equal to n minus 1. So this is for the connected graph. If I have a graph with n vertices and k components, then rank of the incidence matrix is nothing but n minus k. If graph G has n vertices and k components, Then rank of incidence matrix A of G is equal to n minus k. Remember one thing, in the incidence matrix of a connected graph, if I remove any one of rows, then the remaining n minus 1 cross E matrix is called reduced incidence matrix. Reduced incidence matrix. Reduced incidence matrix. In an incidence matrix, if I remove any one of the rows, then the remaining n minus 1 by E matrix is nothing but reduced incidence matrix. And in one more point is, if I have a square matrix in which all the rows are linearly independent, then we call such matrix as non-singular matrix. Call them as non-singular matrix. So the reduced incidence matrix of a tree is non-singular. Let us see how it is. We say matrix is non-singular if all the rows are linearly independent. So when I take a reduced incidence matrix of a tree, say suppose tree has got n vertices and E edges. E number of edges is nothing but n minus 1, right? So for a tree with n vertices, n minus 1 edges are there. So when I take its reduced incidence matrix, then it is of size or of order n minus 1. I have to remove any one row, right? So n minus 1 by n minus 1. Order of the reduced incidence matrix will be n minus 1 by n minus 1. Then the rank of this reduced incidence matrix is again n minus 1. Rank is equal to n minus 1. Therefore, it's a square matrix in which all the rows are linearly independent. Rank is n minus 1 means all the rows are linearly independent. Hence, I can say that it is a non-singular matrix. Therefore, reduced incidence matrix is non-singular. So remember this point, if I take a tree, then the reduced incidence matrix of a tree is non-singular. In fact, I can say that the reduced incidence matrix of a graph is non-singular if and only if it is a tree. Next thing is submatrix of A of G. Submatrix or submatrices of the incidence matrix A of G. If I take G as a subgraph of G, then A of G is incidence matrix of graph G and A of capital G is the incidence matrix of A of G. Then A of G is called submatrix of A of G. This is the main graph and this is the subgraph. Then A of G is the submatrix of A of G.